This is problem number 9 on the sample test problems for test number 1. Consider the function f of x pictured. Assume the domain of this function is all real numbers and that all relevant features of the graph are shown. A, for what values of x is f of x not continuous? So roughly speaking, a function is continuous if you can draw it without picking up your pencil. And so this function I will draw right here without picking up my virtual pencil, which means because I could draw it without picking anything up, we will say that f is continuous everywhere. Part B, for what values of x is f of x not differentiable? So one of the problems with differentiability happens at corners. And so this part right here is going to be a point where f is not differentiable. You can see that because I'll just draw some little tangent lines. So there could be a tangent line there and there and there and there and there. And I already have maybe a problem if it's like a vertical tangent line right there. You know, I mean, that's enough. It's just, it's a very rough transition going from the left side of 0, x equals 0, to the right side of x equals 0. So this function is not differentiable at x equals 0. And we'll just highlight here, since there is a corner or a cusp at x equals 0. Part C, for what values of x is f prime of x less than 0? So we'll just translate this. We know that if f prime is negative, then the function is decreasing. So this question is really asking, where is f decreasing? And you can see from the picture that f is decreasing for all of this part, and then as soon as you go to the right, it starts to increase. So that means that f is decreasing for all the x's less than 0. And if you wanted to write that in interval notation, you would say from minus infinity up to 0. And I'm putting parentheses there instead of the closed bracket. And I also didn't put less than or equal to. I just put less than. Again, because of our answer in part B. The function is not differentiable at x equals 0. So I don't want to say that the derivative is negative. This is simply not true at x equals 0 because the derivative doesn't even exist at x equals 0. Okay, and then finally part D, for what values of x is f double prime of x less than 0? So before I look at the picture, I'll translate this again. So f double prime has to do with concavity. This question is really saying, where is f concave down? F double prime less than 0 means f is concave down. So where is this picture? Where is this function concave down? So it sure feels to me like it's concave down everywhere. We have 4 basic building blocks for most of our graphs. 1, 2, 3, and finally 4. And the ones that are concave down are this one and this one, concave down. The other 2 are concave up. And those 2 in the middle are exactly the 2 pieces that make up f. There's that part, and then the other part. So it feels like f is concave down everywhere. The only little tricky point here is, well, is f double prime negative at the origin at x equals 0? So we'll say f double prime is less than 0 for all x. But at x equals 0, we've already established that the derivative doesn't even exist. So if the first derivative doesn't exist at x equals 0, then certainly the second derivative doesn't exist at x equals 0. So it can't be negative. So we'll say for all x except x equals 0. Since f prime of 0 does not exist, f double prime of 0 also does not exist. And if you wanted to write this in interval notation, you'd say minus infinity up to 0, not including 0. And then the fancy symbol for, I've got another set that I'm going to list here, is kind of a capital U for union. and it goes from 0 to infinity, again, not including 0. So that's the interval notation way of saying all the numbers except for 0.